Today we're going to talk about maximizing drive performance with power module reconditioning. And we will go over an overview of the Toshiba medium voltage drive, talk about storage and startup, because maximizing drive performance starts from the beginning. We'll talk about the power module container. We'll go over an overview of the power module, and then we'll talk about power module reconditioning. Toshiba manufactures different types of medium voltage drives ranging from 2400 volts to 6900 volts and 300 to over 10,000 horsepower. We also have indoor and outdoor units and options for up to 13.8 kV. For those who are interested in finding out about our offerings, you can contact the factory to learn more. There is a single line diagram here showing the components in the Toshiba medium voltage drive. Starting from the input, we have lightning arresters, which protect against shocks to the input voltage. We have an isolation switch, which is the main point of isolation for the drive, and it has open. It grounds when open. Then we have input fuses, which are for short circuit protection, followed by potential transformers, which supply voltage to the controls. Then we see the input contactor, which provides power to the rest of the drive, followed by a pre-charge circuit consisting of a subcharge reactor and a contactor, which bypasses that reactor when the DC bus voltage gets to a certain level. Purpose of that subcharge reactor is to limit the inrush from the transformer. Then we have the multi-pulse transformer, which provides power to rectifiers and the rest of the drive, and also with a tertiary winding that provides voltage 480 volts to the drive cooling fans. Talked about the rectifiers. Those are connected to the fuse secondary, the transformer, and then connected to the inverter section, which consists of the power modules. On the output of the modules, there is a ground fault detection board for sensing ground current, and there are options for filtering of the output, such as a sine wave filter or a DVDT filter. And before we have Hall CTs, which sense current. Showing you a single line diagram, and then here are pictures showing these same components. This is a frame one drive represented here, and you can see the input power connections. That's where the lightning arresters are in this drive. The PTs I mentioned, so those red boxes, the contactors and fuses, then the isolation switch, as well as that self-charge reactor, which we also call the pre-charge reactor. The input transformer, it's that multi-pulse transformer connected to the rectifiers and fuses in front of it. And then the inverter section, which consists of those three power modules And there is a door switch for safety to make sure that power is disconnected or de-energized when the power module doors are open. We have the exhaust fans, which pull air in from the bottom through those air intake filters and exhaust at the top. And then the low voltage compartment, which we also call the control section. That has all the boards and controls for the drive. Then finally, narrowing down to the power modules, they rack in and out easily for maintenance. And for the bigger drives, we have a rollout truck assembly specifically for rolling out those modules, which can be quite heavy. Now to storage and startup. As I mentioned, maximizing drive performance starts from how it is stored and handled. It's important to follow best practices for transportation, for storage, and long-term storage, making sure you use an air ride trailer for transportation so components are not damaged or jarred loose before even getting to site, making sure the drive is kept upright at all times, and using proper lifting techniques when moving the VFD. Dropping a VFD will not be a good way to maximize drive performance. Storage, if needed, should be in a cool, dry location, should not be subjected to extreme temperatures. And for long-term storage, the regular storage rules apply. In addition, we recommend periodically applying control power to the power modules to make sure that the boards with electrolytic capacitors are getting a charge. We would say once for 30 minutes every 2 years would be enough. So here are some examples of the effects of improper storage. You can see some damage to the fiber optic cables, foreign material getting into the modules. And what makes these type of effects dangerous are the fact that they would not necessarily show up right away. These are things that could lead to problems further down the road, which would in turn ultimately reduce the drive life or worse, cause damage. So part of the advantage of a proper startup is to catch some of these things, during the beginning of the drive operation. Proper inspection of the installation, making sure the drive is installed properly, making sure the cables are connected in the right locations, making sure they're, secure and tight, making sure the programming is correct, the protective functions are working, and then the drive is tuned for the correct motor that's connected to it and the application, so that ultimately the drive performance will be maximized because it has been set up correctly. All these steps are best when done by TIC authorized personnel to make sure that you're getting the best out of the startup. And so talked about storage and startup, and now we'll talk about the power module container. I mentioned about applying control power periodically to the power module. One way to do that is with this power module container. It was developed specifically or originally for the power module rental service to make it easier to transport the modules multiple times versus the standard crates, which are better for one-time use. But they also have the additional use of storing the power modules, especially for long-term storage. The containers are built with metal, making them sturdy, which is good for that use case I mentioned of shipping the modules. And there are additional features such as space heaters and control power that could be added to the module. And with this option included, you can plug in the power module into wall power to make sure that the boards are getting charged periodically, and you're making sure that the temperature of the module is properly regulated. Now we'll go over the power modules in the Toshiba medium voltage drive, which are highlighted as shown on the screen. The power modules are characterized by frame sizes, which represent the different horsepower and voltages that we have available. This is not an exhaustive representation of every power module that Toshiba manufactures, but the idea is to give you, a good list of what we have. Starting from the left, there's the frame 2, A2, which is the power module used in the 2.4 kV drive up to 500 horsepower. The A4 micro, that's a 4160 volt power module that goes up to 600 horsepower. We have the frame 0. You notice that there's an A and a B. And this is for the 4160 drive up to 1,000 horsepower. The A is the early version and the B is what we manufacture currently, though you can still see both in the field. Difference is in the heat sink and the way the modules are cooled. Same with the frame 1, which is the 4160, but goes up to 2,000 horsepower. There is the A and the B, and you can see the physical differences, and most of that has to do with cooling of the module. You have the frame 2, which goes up to 3,000 horsepower. Frame 3 up to 3,000, and then the frame 4 up to 6,000. Notice that the higher the horsepower, the bigger the power module is. And mostly the components are the same in each of these. And I'll go over these components. So most and almost all see it's a question. Okay, let me take that, Jason. Maybe put the question in chat so I can answer it. I'll come back to that. Let's see. So with the components in the power module, they are mostly the same in all the power modules. And I've shown them here. First is the oil field capacitors. These should last 20 years or longer. And these are for filtering the rectified AC voltage. We have the power devices shown there. These are the clamping diodes and the IGBTs. The clamping diodes are to make sure that the power modules all reference the same neutral. And the IGBTs, of course, are what switch to generate that AC voltage from the rectified DC. We also have fiber optic cables and wires, connected to the different devices, the boards, the IGBTs, and all of these are for transporting or carrying signals to ultimately the drive control board, which is where they will all end up. All power modules will have different boards. Just have an illustration here, but those boards, go range from the optical link board that takes this fiber optic signals and translates them to electric signals. The IGD boards, which are for firing or turning on and off the IGBTs. There's a power supply board, and there's the boards for detecting the voltage. So all power modules will have, these boards, and they're mostly the same, except the boards that turn the devices on. Then finally here, showing the heatsink, which is what cools the power devices. This shown here is a heatsink for frame 4 power module. So this is a bigger heatsink. Made a note there about the IGBTs. They're rated for 3300 volts. So they are actually medium voltage IGBTs. Though the maximum voltage that they will see during normal operation is 1800 volts. So there is a lot of safety margin built into the IGBTs. So these components represent majority of what makes up the power module. Something I did not show here is a temperature switch, which is used to sense temperature, which is mounted on the heatsink and will open if the temperature gets above 90 degrees C. Here is showing an example firing pattern to show how the power modules are connected and the power devices. And there is an output voltage signal of each of the 3 power cells. So I mentioned earlier, there is a clamping diode that makes sure all the power cells are referenced to the same neutral. You remember power modules rack in and out for maintenance. And the beauty of the Toshiba medium voltage drive is that the power modules can be racked out by, the customer technicians. It is not necessary to have a Toshiba field engineer go to site to pull out the modules, though some customers still prefer that. There are instructions on the door of the power module explaining the steps to pull them out, and mostly involves disconnecting the cover for the control cables and the bolts for the cables that are connected to the module, and the bolt that holds the module to the frame. Depending on the frame size, the bolts are located at different places. And then the module racks out. For this particular example, which is a frame 3 4160, the module can be racked out onto the truck assembly I mentioned, which we sell. And then there is a ramp that can be attached to that truck assembly for rolling the module onto the floor. And the lifting bracket attached to the module can be used to lift it to and from wherever it needs to go. And as I mentioned, this label is on the drive for those who have questions about it. Now we'll talk about power module testing. Testing of the power modules is also relatively straightforward. It can be done with a multimeter using the diode setting of that multimeter. you need to connect it to the bus as shown in this picture, following the table for where the positive and negative lead should go. And in this example here, we're measuring between the P and the common, and the value should be between 0.6 and 0.8, which, here it's 0.692. This tells us that the devices between those connections are good. And so you follow that same sequence going down the list and record the values to make sure they match what is expected. Following the testing and troubleshooting theme, I've included a slide here on what to do on just 2 faults that you could encounter in the field. First step, anytime you have a fault on the drive, is to always download traceback data. You want that data recorded because the drive has a limited number of registers to store faults. And so eventually the data will be overwritten. So if you store it, then you'll have it for future reference. Next step is to lock out the drive. Follow your lockout procedures to make sure that the drive is isolated. So first fault there is the OCD, overcurrent device. And it follows the format shown there. The asterisk refers to the phase that is affected. So it'll be U, V, W, and that's starting from left to right if you're looking at the front of the drive. And it goes from A1 to B4, which is A1, A4, B1, B4. So if you were to see a fault like this, after you've downloaded the traceback and locked out the drive, first thing you want to do is perform static checks on the identified phase. So if it says OCD U1A1, you want to focus on the U phase and perform the static checks I showed in the previous slide. If all the readings match the expected values, that is good news. It means that for the most part, none of the power devices are damaged. And so you now inspect and look for anything visibly out of place. Maybe a cable disconnected or fiber optic cable not secure. And finally, this is probably going to be confirmed at startup, but if there's any doubt, you want to make sure that there are no capacitors in the motor terminations. There should only be cables in the motor termination box. That's just a quick overview on troubleshooting an OCD fault. Next, overheat, power module overheat. That's OHT. And as I mentioned, the asterisk refers to the phase that's affected. First thing to do, if you see overheat fault, after downloading the traceback data and of course locking down the drive, is to inspect the power module heatsink for cleanliness. A clogged power module heatsink, like shown in the picture on the left, will cause an overheat. It might not be right away, but eventually, because airflow needs to be unobstructed through the heatsink to make sure that the power devices are properly cooled. And this fault will be detected by the temperature switch I mentioned. One of the things you can do if you have doubts about your heatsink is you can shine a light through it as shown on the right, making sure that that light is visible at the top. So if the heatsink that is clean and free of obstructions, you should see the light come through properly. Next thing is to make sure the fans on the MVD are properly operating. And I mentioned that the transformer provides power to those fans. So if they are not operating, or if they are operating backwards, that can cause a power module overheat because power devices need proper airflow. And finally, the air filters that I mentioned also need to be cleaned. Any obstruction to those can also cause a power module overheat. So these are some tips for troubleshooting a power module in your site. Next, we'll talk about power module reconditioning, which is the service we offer to help maximize the life of the power module. And we'll see how it helps with the next few slides. This service is available for power modules in use or spare unpowered modules. We have had countless examples of customers who have had modules for 10 years or more in their warehouse, never used because of the inherent reliability of the Toshiba medium voltage drive. And our experience is most people do not have special warehouses specifically for power modules. The warehouse is usually for everything they have at the site. And so you might have situations where the power modules are not stored in the best conditions. So with the power module reconditioning program, we can help in those situations. The options available are basic reconditioning and the advanced. And what level of service applies will depend on factors such as the age, the physical condition, and or runtime of the modules. A module that's 10 years old but not run, maybe run only once a week, might require a different service from one that's run 5 years, but it's 24/7 operation in the cement plant. So these recommendations are general, but it could be specific recommendations based on your specific situation. So in general, we recommend the basic reconditioning, for modules after 5 to 7 years, the advanced after 8 to 10 years in operation. All the reconditioning options include a 1-year protection plan at no additional charge. This 1-year protection plan covers the entire module, not just components we replace. So it's essentially the same protection as you would get on a brand new module. Another additional benefit is the inspection fee for inspecting a module that has had a fault in the field is waived, regardless of if that fault will be covered by the protection plan. So it's just an additional, you can say hidden benefits that if that module is covered by the plan, it can be sent in and inspected at no charge. A good example is, maybe a module has been reconditioned and for one reason or the other not stored properly, which can happen. And in that situation, the module might need to be sent back because now there's doubts about its operation because of the storage means. In such a situation, normally the inspection will not be charged because that is not a covered situation by warranty. But because this is the Toss Care Protection Plan, that inspection will be charged. So in a case where it's sent in like that and there's nothing wrong with it, then no charge to the customer. To further expand on the benefits, the included protection is for 1 year, but it can be extended to 2 years. This also helps with improved reliability through scheduled maintenance. We all know, as mentioned, the drive is inherently reliable, but different external factors can affect that, and reconditioning will help minimize the effect of these external factors. Of course, improving reliability will reduce the risk of unplanned downtime, which ultimately is about reducing repair costs. And finally, most importantly, this service helps to extend the life of both the drive and the power module through renewal of critical components. Replacing these components with new ones is a way of also resetting the life of that power module, which in general is 20 years, even though we have modules older than that still operating today. So here is to give you a picture of what happens to a module when it comes to the Toshiba repair shop. Yeah, first is that the module is inspected by a technician to verify that it is in good working condition. Remember that the reconditioning service is preventive, which is different from a repair. So the goal is to make sure that the components that are now being replaced are still functional and will last. And so we apply control power to verify the board signals after inspecting the components. And then the module is tested with full voltage to make sure that it is operational. In some cases, like the example shown here, the module might not be in the best condition to put into the test stand. And so some preliminary work might be done to it, such as light cleaning and, making sure all the connections are properly connected. Once the module has passed that initial test, then an assembler will clean the module, which is a big part of the reconditioning program, as we've gotten to see, is that foreign components are a danger to proper operation. And so the assembler will actually disassemble the module, clean, especially the heatsink, which is on its own a process to clean, and then replace the components, which I'll go into a little more detail in the last slide. And then after this is done, a second assembler will QC the work of the first assembler, making sure that everything is connected, nothing is loose, nothing is missing. And then it goes back to a technician to inspect the module again, perform control power tests similar to what was done before the work started. And then finally, the module will be tested with full voltage first. So no load, but full voltage, making sure that all the signals are good and that the power devices are functional. And then it's going to be full current test so that we know that the module can handle the rated FLA. And then finally, an overload test. Make sure that the module can handle an overload condition without damage. And so after all of this is done, we know that this module will work in the field and the customer can have confidence in what we've done. And an example of a real life module is what we're showing here in the before and the after. No, it's hard to tell, but these two pictures are the same module. Even though that power device looks white in the before, it actually is a black device that was just covered in a lot of dirt. And so this is an example of what we're doing in the shop. And the last slide here is a summary of what we're doing, what we're replacing for the three different levels of reconditioning. First, as mentioned, is the inspection of the module. We're replacing the fiber optic cables. If you remember, that's a key part of the power module. The IGD boards, these are the boards for turning the IGBTs on and off. They're connected directly to them. And these have electrolytic capacitors, which is why we replace them if the module has been on the shelf for a long time. We also replaced the power supply board. That's another board that has electrolytic capacitors. And then all the levels include the full factory testing, the 1-year protection plan, and the option to extend that for a second year. So that's the basic. The basic plus adds extensive cleaning. So the steps I mentioned in the previous slide were for an advanced, which is where the module will be disassembled and cleaned. That is also done with the basic plus reconditioning. In that case, we do not replace the power devices. We just reapply thermal compounds to make sure that there's proper heat transfer between the power devices and the heatsink. So that's the difference between the basic and the basic plus. This is extensive cleaning and highlight that here, extensive cleaning and reapplying the thermal compound. And lastly, with the advanced, we're doing everything we do in both the basic and the basic plus, but in addition, we are replacing those power devices. So here it's more extensive rebuild of the module. And again, all these options include the 1-year protection plan and not just the components we replace. The whole module is covered. And the idea is that you are getting a module almost like a new one and should operate the same way and last almost like you bought a new module. And that's everything I have for today. Thank you all for listening. And now I'll look at the questions and see if there's anything left to answer. Yeah, I see a question from Michael Todd. How does Toshiba handle situations for improper installation? For example, customers drilling holes into the cabinet for wiring accessories. It depends on what damage this will cause. You know, in some cases, the drilling of the hole might not have caused any significant damage. And in those cases, you know, we just point that out to the customer and, you know, continue with the startup. If it has caused damage, you know, maybe they've gotten metal shavings into the transformer. In that situation, then, you know, the transformer will need to be replaced. So it depends on what the situation is, but ultimately we will rectify it before the commissioning can go on. See a question about the alarm. So an alarm for the temperature of the power module. It is not, it's not adjustable because this is a switch that comes on and off. So once it hits that temperature trip point, it will open. I mean, one option for this is adding uh, a an RTD to the cabinet, which you can use the temperature of the cabinet as a proxy for how hot the drive is getting. And yes, believe this video will be made available. The current turnaround time for power module reconditioning right now is in the 3 to 4 week range. So if a module is sent now, you will be getting it in that 3 week range based on the loading in the shop. And I see Jason, do you have a question you want to put in the chat? Doesn't look like because you still have your hand raised. Okay, it's a question about why is reconditioning needed when they are working properly? And that's a good question. It's a maintenance recommendation in when the power modules are working properly, you can make a good case that you don't need to do anything. It's more trying to prevent a future event. And we came up with the recommendations based on data from our repair shop on modules that had come into us. And we saw just based on the environment, there, certain components that are affected more than others.